Hello students, welcome back to NKG Online Study and E-Learning platform. Today we are going to learn case statement hardware supernova, the secret weapon of FPGA engineers. Imagine your FPGA receives a 2-bit signal 00011011. Four possible choices. Easy. You could write if cell 2 hashtag tick B00, else if cell equals to 2 tick B01, else if cell equals to B2 tick B10, else if cell equals to 2 tick B11. Works perfectly, but now imagine 16 options, 32 options, 64 options. Your code starts looking like a horror movie. And that's exactly why professional FPGA engineers use a superpower, a tool so common that you will find it in CPUs, communication system, FPGA designs, and ASIC chips. Today you are learning the case statement, and trust me, once you understand it, you will never want to write huge if else chains again. Let's be honest. Long if else chains are painful. You keep scrolling, you keep searching, you keep asking. Hard to read, hard to debug, hard to scale. Error prone for large designs. Where is the condition I need? You keep asking. As projects grow bigger, readability drops, debugging becomes harder, mistake increase, productivity falls, and engineers hate unnecessary complexity, so they look for something cleaner. Imagine selecting one of the several outputs. Many beginners write if, else if, else if, else if. Again and again and again the code works, but the design becomes difficult to manage, especially when the number of choices increases. This is where case shines. Think of case as a menu. You provide one selection option. The hardware chooses the matching option. Simple, organized, professional. Instead of asking, is it this? Is it this? Is it this? Case says, show me the value. I will choose the correct option. Much cleaner. One selection input controls output. Easy for engineers to understand. A simple case looks like this. Case cell 2 2 tick B00 y equals to A, 2 tick B01 y equals to B, 2 tick B10 y equals to C, 2 tick B11 y. One selection, signal, multiple choices, one matching results. That's the entire idea. Simple enough, but the hardware behind it is powerful. Imagine a TV remote. You press 1 news, 2 sports, 3 movies, 4 music. The TV doesn't check hundreds of conditions, it simply selects the correct channel. Case works exactly like that. One value, one selection, one result. That's why engineers love it. Traffic routing decision also there. Internally, the hardware does something very simple. Step 1. Read the selection signal. Compare it with the available options. Find the match. Generate the corresponding output. No software execution, no thinking, just hardware logic. Hardware doesn't execute code. This is another HDL mindset movement. When beginners sees case, they imagine software execution, but synthesized tools see something different. They ask, What hardware can perform this selection? Because Verilog is not software, it's hardware blueprint, not software execution. Hardware logic is created, and the blueprint must become real circuitry. Here comes today's mind-blowing moment. Most case statements become multiplexer, real multiplexer, physical selection hardware inside your FPGA. The case statement is not running. The case statement becomes hardware. That's the HDL magic. Imagine four inputs A, B, C, D and one output. Why? Selection which determines which input reaches the output. This is exactly what case does. One selection signals many possible outputs and one final result. This is, you can have one example. Now let's compare if, else and case. If else checks conditions sequentially. Case matches specific values directly. Both create hardware. Both are important, but they solve different problems. Choosing the right tool is a part of becoming an RTL engineer. The priority differences. This is extremely important. If else creates priority, example, if A, else if B. If both are true, the first condition wins. Case behaves differently. Case is value based selection, not priority based decision making. This distinction appears often in interviews. Where is case used? Almost everywhere. CPUs use case, instructions decoder use case, control units use case, communication system use case, state machines use case, address decoders use case. Once you start reading professional RTL code, you will see case constantly. Ever wondered how a professor understands instructions? Imagine 0001 add 0010 sub 0011 multiply 0100 divide. The processor must decode the instruction. One value, many possibility, perfect case statement application. In fact, modern processors contain thousands of case-like structures. Used industry usage, used in CPUs, common in FPGA projects, found in ASIC designs, used in communication systems. The common mistakes usually an engineer do, that is, many beginners write case bracket SCL and case without default looks harmless, forgetting default branch. Undefined output behavior, unexpected synthesized result, hard debugging later, but it can create serious problems. What happens if an unexpected value appears? What happens if none of the cases match? Who assigned the output? Nobody. And that's when synthesis tool may infer unwanted hardware, possibly even latches. That's why professionals almost always write default. Safety first. Always include default, cover every valid state. Keep formatting readable. Write maintainable RTL. Use meaningful labels. Make hardware intent obvious. Good RTL isn't about clear code, it's about predictable hardware. Suppose an interviewer asks case or if else, the correct answer is depends. Need priority, use if else. Need many values, selection, use case. Both are important. Great engineers know when to use each tool. Today, we learned case simplifies large decision logic, case often becomes multiplexers, case improves readability, case is used in CPUs and FPGAs. Default is extremely important and most importantly, case does not execute. Case become hardware. Take a moment and look at how far you have come. You now understand. We have made RTL foundations completed. Now we are ready for our introduction to HDL syllabus. Ready for Unit 1. We have covered Video 1. Why HDL exists? 2. How hardware thinks. 3. How hardware remembers. Why clock exists. Event-driven hardware always blocking versus non-blocking. Continuous assignment wire versus resistor if else in hardware. And in this video, we have covered case statement hardware supernova. This is no longer beginner territory. You have built the exact foundation required to understand real RTL design. And now the real syllabus begins. In the next phase of this playlist, we enter Unit 1, not just syntax, not just examples, real HDL modeling concept used by engineers. The topics you have learned so far will finally connect together into complete digital system. So if you are enjoying the RGPV HDL playlist, ED302, hit subscribe button and join the journey because from the next video onward, you are no longer learning individual HDL concepts. You are starting to think like a real FPGA and VLSI engineer. Thanks for watching.